Okay, we'll discuss now. We'll continue our discussion. Excuse me. We'll continue our discussion about single sideband modulation, which we started yesterday. So, if you recollect, what we said was that we don't have to transmit both sidebands as we do in DSP-SC or DSP-AM, right? Because information about the baseband message signal is available in any one of the two sidebands. So, we could decide to cut off either the lower sideband or the upper sideband, right? And the basic advantage that we will achieve by doing so would be increased bandwidth efficiency, right, and also power efficiency. We will be transmitting less power, right. So, well basically power efficiency is secondary, main thing is the bandwidth efficiency. So, just to recapitulate once again, in terms of the frequency domain, if this represents the spectrum of your message signal, these are the two sidebands of the normal AM signal shown here in dotted lines, right. So, this is the normal DSP-SC spectrum, right. What we are saying is we can remove one of the two sidebands. For example, we could remove the upper sideband, right, and transmit only the lower sideband. So, we are transmitting this. This will of course come along with that, right. So, this is around F sub C and this will be around minus F sub C. So, this portion of the spectrum is being filtered out at the transmitter. You generate from here to the DSP, first generate the DSP-SC signal, and then by a suitable sideband filter like we discussed yesterday, you go through the normal modulation process first, and through a suitable sideband filter eliminate one of the two sidebands. If you eliminate the upper sideband, you are transmitting the lower sideband, and this, for eliminating the upper sideband, you can use a low pass filter or a band pass filter whose pass band is from FC to FC minus B, right. If you want to transmit the upper sideband, you have to use a high pass filter or a band pass filter whose transfer function is non-zero between FC to FC plus B, right. So, that's how you will choose a sideband filter. And like we discussed, the reconstruction is possible by the same process that we have for the DSP-SC signal. So, here is your SSB signal coming in, right. So, this is your SSB spectrum, this is the SSB signal in time domain. You again multiply with the carrier and pass it through a low pass filter, just like what you were doing for the case of DSP-SC, right. In the frequency domain, what basically we are saying is that as a result of this multiplication, the same frequency translation is happening again. This part of the spectrum will come here, right, and this part of the spectrum will go here, and because of the symmetry, it will be precisely the same MF that we started with, right. So, of course, there will also be translation around 2FC and minus 2FC, but that will be eliminated by the low pass filter. So, the reconstruction process in the time domain as well as in the frequency domain follow the same principle that we had for the case of DSP-SC, the double sideband suppressed carrier modulation, right. Now, so far so good, but suppose let's look at okay, before I come to that, what are the advantages that we mentioned of doing this? The main advantage is power bandwidth efficiency. Your transmission bandwidth B sub T is now not equal to 2B, which was the case for the two previous modulations we discussed, but simply equal to B. So, in the same bandwidth now you can transmit twice as many messages as, so you can transmit two messages in the same bandwidth rather than in the 2B around FC rather than a single message, okay. That is the main advantage. What is the power that will be transmitted in the SSB signal? what was the power that was being transmitted in the DSBSC signal? If you remember the expression, it was S sub C into S sub M, which was the carrier power into the message power. So in this case, how much will it be? Divided by 2, because you are removing one of the sidebands, right? Okay. Let's discuss briefly the issue of practical realization of the SSP waveform. The practical realization would require that you have a suitable set. The additional thing that you require on top of what you do in DSPSC is this sideband filter, right? Now, this is a non-trivial operation that you want to do. This is what you need to understand. You require a sideband filter with almost ideal characteristics. Suppose you decide to retain the lower sideband, right? So what kind of transfer function should the filter have? Let's say you do it through a low pass filter, right? So what kind of transfer function would the low pass filter have? It should have this kind of a transfer function, right? It should have a perfect transmission up to the carrier frequency FC, right? And zero transmission immediately after that. And you know that such an ideal low pass filter is almost impossible to realize, very, very difficult to realize. In practice, of course, you will not realize a low pass filter, you realize a band pass filter, which will have this transfer function, but it will also be associated with the same difficulties, right? One can approximate such filters. Basically, you require what are called high Q tune filters, right? You require, because typically these carrier frequencies are very high, right? And this bandwidth will be a very, very small fraction of the carrier frequency. So a narrow band high Q tune filter will do the job, right? You understand the quality factor of a tuned circuit, right? Quality factor determines how much bandwidth you have around FC. The larger the quality factor, the lower the bandwidth, right? A large quality factor, a high Q filter will mean a very sharply tuned filter, right? For ideal tuned filter, the Q is infinity, but as Q becomes finite, as it becomes smaller and smaller, the bandwidth increases, right? So you require a Q of a suitable value, and typically because of the fact that you require very sharp cutoff, you require fairly high Q filters, right? You require very high Q filters. And designing high Q filters, high quality factor tune filters using conventional passive components like inductors and capacitors is extremely difficult, right? They would be typically very large order filters, and remember, no matter what you do, how ideally you construct your inductors and capacitors, there will be losses, right? There will be losses due to the resistance of the inductor or various kinds of losses in the capacitor, right? And these losses is what reduces the quality factor, right? If you don't have these losses, you can have the ideal tune filter, but because there are losses, the frequency response gets flattened and you don't get a very sharp Q filter. On the other hand, there are devices, there are materials which enable the realization of these high Q filters, right? For example, I'll just mention the name here for your information. You could use what are called piezoelectric crystals, or rather piezoelectricity is not important here, so I think I should remove this thing. Quartz crystals is the more appropriate point. You can use quartz crystals, right? And interestingly, they have some very, very useful electrical characteristics, and they can be used in the resonance circuits of tuned circuits to provide you very sharp frequency response, right? So you could get the kind of filters that you want to design for the SSP generation by using quartz crystals. So you will use quartz crystals in the band pass filter of the for sideband filtering. More about this later if we get the time. At the moment, I just want to mention this fact because I don't want to get into a discussion on how quartz crystals work in this connection. Yes, please.
So you said that using the single sideband modulation, we can actually reduce the bandwidth, as in terms of 2B to 1B.
Right.
So, but the thing is, we still are transmitting in that region. We just are removing it via at the receiver via a filter. Suitable.
No. This sideband filter is at the transmitter. This is the transmitter. We are putting the sideband filter before transmission. Right? Please understand that. At the receiver, I am doing exactly what I was doing for the DSB-SS signal. The receiver is no longer not different at all. That if that was another case, then there would be no advantage. So this is the transmitter, right? So you are putting the sideband filter at the transmitter. Please understand that. Okay. So one can use this specially designed, properly designed quartz filters, quartz crystals filters, which have these very interesting properties of providing you very sharp cutoff or very high Q characteristics. Okay, but we'll discuss more about that later if the time permits. Now, before we proceed further, let me ask you a question. Suppose I ask you, tell me what will this waveform look like in time domain? Can I write a mathematical expression for this waveform in the time domain? The answer is not that easy anymore, right? Because I can write the expression here. That is simply the product of these two waveforms. But what is the kind of waveform I have after this single sideband filtering is not so obvious. Now we'll take that up as the next job to do, and when we do that, we'll find that once we have this mathematical expression, it also provides us another method of. It also gives us another method of generating SSP signals. Yes, please.
Anyway, we cannot transmit anything between that FC minus B and FC plus B, because if we transmit anything between that, when we actually frequency translate it back, when we demodulate it, then it will interfere with the two.
Between FC minus B
and
to?
FC plus B.
So what is the question?
So
We can't transmit anything during this interval?
In this we cannot we are saying that we are gaining on the bandwidth. Bandwidth.
Yes, because I am using the bandwidth from FC to FC minus B.
No sir, if we use something, if we put in something like an impulse.
I could. Let me clarify your doubt. I think the question is, can I use this bandwidth or not? Can I use this message bandwidth or not? Yes, of course I can. I can put another message in this bandwidth. Suppose, in fact, this is when I discuss frequency division multiplexing with you later, we'll see that this is precisely what you do. These are the advantages that you derive from SSP. You can put different messages, each of them occupying only a bandwidth of B, close to each other, right? Adjacent to each other. I can put one message here, another message here, a third message on this side, a fourth message on this side, and so on and so forth. I can put them side by side at a spacing of only B hertz. There are methods to do that, right? And I can do that precisely because each of these messages requires only B hertz, right? So that is the advantage of SSP, and if there is an application, we should use that advantage, right? Otherwise, what's the point? If I'm not going to use it, then what's the point? Of course, the whole idea of saving it is to use it somewhere else.
So, but in this case, if we use it, there is actually an interference between the wave in the frequency domain between the time.
How there is an interference? I'm eliminating this from this message.
So if,
I'm putting another message in that
if we are
spectrum.
transmitting something else from FC to FC plus B.
Yes. So where is the interference?
So then when we translate it, then the two waveforms will
Obviously, at the receiver, you'll have to separate them out. Okay, I understand your doubt now. At the receiver, if I see, you want, what is the idea? Idea is to be able to share the same physical medium, right, in terms of bandwidth. So that you do by putting multiple signals in different adjacent bands. Obviously, at the receiver, you must make sure that you demodulate only the right signal for you. right? You'll have to do a separation, corresponding separation, filtering at the receiver, so that you only see one message signal at a time, right? Otherwise, there will obviously interference. I hope that answers your question. All those things will become clear as we proceed. But these are questions that you must ask, and so that things get clarified. So let's return to the issue that I just raised, and that is representation of single sideband signals. Okay. So let me start afresh on a fresh page, and let me draw a few diagrams so that we can work with these diagrams. I want to write an expression for the SSB waveform in the time domain, but to do so I'll start with the frequency domain, because SSB signal is very easy to understand in the frequency domain, not so easy to understand in the time domain, right? So let me start from where it is easy to understand, right? And let us say as we know, we can generate an SSB signal by starting with a DSP-SC signal, right? And then low pass filtering the. So I must multiply the message waveform, a message spectrum which looks like this, with, let's say, the transfer function of an ideal low pass filter which looks like this, and that will give me the lower sideband signal, right? So this will generate. So this is X DSB in the frequency domain. The corresponding X SSB spectrum would therefore look like this. Right? After this low pass filtering. So this is the process through which the SSB waveform is generated in the frequency domain. Right? Multiplication of the DSP-SC spectrum with the transfer function of this kind of an ideal low pass filter, right? So now let's look at this ideal low pass filter. I can represent this ideal low pass filter as the sum of two signum functions. This is minus FC, this is plus FC. Can you see that? I can represent this rectangular function which specifies the ideal low pass filter as the sum of a function like that, right? And a function like that. This is, if you were to express this in mathematically in terms of the signum function, how will you write this? Signum of, where is the signum function located here? Minus FC. So this will be signum of F plus FC, right? And this will be correspondingly signum minus signum of F minus FC. If I add up these two functions, right? Of course, let's say take the amplitude as half, so that after addition, this will give you 1 here, right? So this will give you a filter, the ideal low pass filter that you are looking for, with a transfer function value equal to 1 between minus FC to plus FC, and 0 below minus FC and 0 above plus FC, right? So if I add up these two functions like this, I get this. Now I am doing this just to do some simple manipulations so that I can write down the corresponding expression in the time domain, right? Okay, so it's clear that I can write this spectrum as the product of this DSP-SC spectrum with this function plus with this function. because that will be equivalent to the product of this with the ideal low pass function. So let me put it down more clearly. So what we are, let me first write this mathematically. What we are saying is that the ideal low pass filter H, this should be H sub LF, is equal to half of signum F plus Fc minus signum F minus Fc, right? So this is basically what I am saying. This transfer function is a sum of these two. Yes, please.
When we are making the amplitude half here, then why we are taking half the amplitude?
It is because this half is there that I'm, so this is half signum F, this is my half, right? I'm adding these two functions and getting this function. That's all I'm saying, right? So, and your, what is the expression for the DSP spectrum? That is half AC MF plus FC plus MF minus FC, right? So what are you doing? You are multiplying this spectrum with this transfer function to produce your SSP output. Agreed? If I multiply this transfer function with the DSPSC spectrum, which is this, I'll get my SSP spectrum. So therefore, my expression for the SSP spectrum in the frequency domain can be now written in a closed form. It will have how many terms? You are multiplying 2 terms in one expression and 2 terms in another expression. You will get 4 terms, and these 4 terms will be 1 by 4 AC. So maybe you can, it's, can you see, is it visible both these terms? Okay, so we can manage with that. So if I multiply this first with MF plus FC, you will get signum F plus F minus plus MF minus FC. So I'm taking these 2 terms and multiplying with this signum F plus FC plus minus 1 by 4 AC MF plus FC into signum F minus FC. Please check it out that I am doing things right, plus M F minus FC into signum F minus FC, right? These are the 4 terms you will get. Okay. Any questions on this? Now, if you look at it carefully, I can collect these terms into 2 groups. Is there a term corresponding to just MF plus FC alone? Which one is this? This term, or which one? Suppose I call this A, call this B, call this C, call this D. Is there one of these terms equal to MF plus FC? It will be this is term C, you see, this is minus half MF plus FC into signum F minus half signum F minus FC is plus 1, right? So this term, this is the term C, right? Similarly, can you identify a term which corresponds to MF minus FC? right. So that is this term, right? And the other two terms, now I have deliberately collected these two terms first, because this together will be the same double sideband spectrum that I started with, plus the other two terms which you can write. So we are taking care of C and we are taking care of B. The two terms which are left are plus 1 by 4 AC MF plus FC signum F plus FC, and which is the other term left, minus M F minus FC, that is, so this is the term A and this last term is the term D, signum F minus FC. Okay, so please look at it carefully and see that is okay with you. Basically what we are saying is that this term, look at this, MF plus FC is which, that is this component, right? MF, sorry, this is your MF plus FC part, right? That when multiplied with this part will produce this portion of the spectrum, right? So sorry, what we are saying is this multiplied with minus half signum F minus FC during this, in this entire interval, this function is plus 1, right? So this into this will be this itself, that's all we are saying. So that is the term C, right? Is that clear? Similarly, the term B, MF minus FC is this part. This into this function at this region would be again this itself, which is MF minus FC. So these two terms one can take out and combine them, put them together like this, and the remaining two terms are here, the term A and the term D. Okay, so I have explained that again. So if that is fine, we proceed further. Okay. So now look at the first two terms. We know that those first two terms will correspond to, can you give me the time domain expression for the first two terms, the sum of these two terms? What is the corresponding time function? Half AC MT cosine omega CT, right? This is a DSPSC signal, that's all. So this is half AC MT cosine omega CT, right? So this is nothing but 1 by 4 AC in the frequency domain MF plus FC plus MF minus FC. However, what the second two terms will amount to is not very clear right now, right? What will be this part of the function is not very clear. So let's try to understand this part. This part is clear in the time domain. Okay. So now let's start with this. This is where the Hilbert transform comes in very handy. Remember, Hilbert transform is defined in terms of the signum function in the frequency domain, and we are having signum functions here. So there is a relevance here of the Hilbert transform, use of Hilbert transform. To start with, recall that in the frequency domain, this is the same as minus j signum f into m of f, right? The inverse Fourier transform would be nothing but the Hilbert transform of mt. You multiply the spectrum of mt with the function minus j signum f in the frequency domain, and that's nothing but the Hilbert transform of mt, right? So we start from here. Now also recollect the basic frequency translation theorem. Suppose you multiply mt with e to the power plus minus j2 pi fct, right? What is the corresponding frequency domain relation? when it is empty plus e to the power plus j2 pi fct, this will be f minus fc. When it is minus, it will be f plus fc. So this is f plus minus plus f sub c. Right? This is your basic frequency translation theorem. Similarly, now if I look at m hat t e to the plus minus j2 pi f sub ct, now can you tell me what will this be equal to? Given that m hat t has this Fourier transform, or first let's talk about the frequency translation. This will produce the same spectrum around, if it is plus here, around minus, right? So this will give you minus j m f minus plus f sub c into signum of f minus plus f sub c, right? Basically the same spectrum on which this frequency translation theorem is applied, right? So now, keeping these three basic results in mind, let's look at the inverse Fourier transform of the last two terms in this expression. What do they correspond to? So if I look at the inverse Fourier transform of the terms 1 by 4 AC into m f plus f sub c into signum f plus f sub c minus m f minus f sub c signum f minus f sub c, which is the last two terms. Now please tell me term by term what do they correspond to. What can I say about this term? Looking at these relations, can I say that this is minus a sub c? Which result will be applicable? This one, right? Divided into 1 by 4 j, right? This 1 by j will come because I don't have minus j here, right? So 1 by 4 j into m hat t e to the power minus j2 pi f sub ct, right? And what about this term now? Same thing, plus a sub c 1 by 4 j into m hat t plus j2 pi f ct, right? Are you all with me? So now if I combine these two terms, what do you get? Take m hat t outside as a common factor, you are left with e to the power j2 pi f ct minus e to the power minus j2 pi f ct divided by 2j, right? So this is nothing but, let me raise it slightly so that you can see it properly, half of a sub c, what will it be equal to? M hat t into sine 2 pi f ct. So I have a closed form expression for the inverse Fourier transform of the last two terms. The first two terms were equal to half AC mt cosine omega ct, and the last two terms are equal to half AC m hat t sine 2 pi f ct. Very interesting. So that gives me a closed form mathematical expression for the SSB signal, the single sideband signal, in terms of the message and the carrier, just like we had for the DSPC signal, and that is equal to half AC mt cosine omega ct plus half AC mt m hat t sine omega ct, right? A very neat and interesting expression. Any questions? I hope you have followed the derivation. It is fairly straightforward. Basically makes use of the properties of the Fourier transform and the properties of the Hilbert transform, right? And what kind of a SSB signal is it? It is a lower sideband signal, right? Now it's a very simple exercise for you to go through the whole process again and show that if instead of plus here I have minus here, you will get the upper sideband signal. Okay, it's a very interesting and useful expression, mathematical closed form expression for the SSB waveform. It's not easy to visualize this waveform, because to visualize this waveform, you not only have to visualize this plus, but also you have to visualize this. Now, for arbitrary signal, one doesn't know what m hat t will look like. For certain kind of signals, one can work it out. For example, for cosine omega mt, I can say that Hilbert transform is sine omega mt, right? But for an arbitrary waveform, very difficult to see what the Hilbert transform will look like, right? So in general, it's very difficult to visualize it, but for specific kind of waveforms, it may be easy to do so. Now this representation, so this is the representation that I was talking about, mathematical representation of SSB signals. This representation leads to a second method of generating SSB waveforms. Right? That's called the phasing method. Right? And it basically implements this equation. That's all. Right? So what you need is, you start with a message waveform mt, and you want to generate this waveform. You just go through the terms of this equation. So you have two branches, mt, you have a carrier component cosine omega ct, right? And that's one branch. In the lower branch, before you do this multiplication, you have to do a Hilbert transformation, which is what? It's a 90 degree minus 90 degree phase shifter for all the frequencies present in MT, right? And that's followed by a second product modulator in which the carrier is sine omega ct, and you simply add up these two to produce your lower sideband signal, right? If you subtract one from the other, you will get the upper sideband signal. So looks very neat and very simple, right? The requirement of, so this is the second method. In the first method, you required high Q tune filters around the carrier frequency to remove one of the sidebands, right? In this method, it looks very simple, but actually that the difficulty still remains. The difficulty has been passed on from realization of a high Q band pass filter to an ideal Hilbert transformer, right? Remember, an ideal Hilbert transformer will have to effect a 90 degree phase shift, a minus 90 degree phase shift for each and every frequency component in the bandwidth of the message signal, right? Starting from f equal to 0 to whatever is the bandwidth, to f equal to b, right? But that's also, such an ideal Hilbert transformer is also not easy to realize, right? However, since the whole operation has to be done around baseband, right? This Hilbert transform is operating on the baseband signal. It's much easier to approximate such a Hilbert transformer than to realize the high Q tune filter that is required for SSB filtering. Both the methods are used in practice, this one as well as the sideband filtering method, right? Both have their pros and cons, but this gives you an alternative, right? So this is a second way of generating the SSP waveform, which is called the phasing method. Basically we call it the phasing method because this requires the implementation of a 90-degree phase shifter, right. You require a 90-degree phase shifter, not at a single frequency. Realizing a 90-degree phase shifter at one frequency is a very trivial job. You can think of a very simple circuit consisting of only resistance and capacitance to do that, right. In fact, ideal capacitance would produce a 90-degree phase shift, right. But to realize it for a band of frequencies is not so easy, right, over the entire band. Same constant 90-degree phase shift. Okay. So that's about the SSP waveform representation and its generation. Obviously, we have already talked about demodulation of SSP waveform to some extent, right? But I like to come back to this issue. The demodulator that I have discussed so far at the beginning of today's class and also mentioned earlier, what kind of a demodulator is that? What do we call it? A synchronous or coherent demodulator, right, which would require us to have a local carrier in phase synchronism and frequency synchronism with the carrier of the incoming signal, right. So one demodulation process is the coherent demodulation that we already discussed. Right. So this we already discussed. Let's consider what will happen in this case when it is not coherent. Remember we did this, carry out this discussion for the case of DSPSA signal, and we understood that due to a phase offset the signal will be attenuated, right, and due to a frequency offset we will see the so called wobbling effect, right. The further modulation of the received signal in time, message signal in time. Sometimes amplitude will go up and sometimes it will come down. The rate of this depending on delta f, the frequency offset between the transmitter and the receiver carriers, right. What will be the case in SSP? Let's look at that, right. So let's look at the effect of, if suppose you are using a coherent demodulator but there is a phase incoherence, what will be the effect? So to do that, now we have the mathematical tools to handle it. We know that I can represent the SSP waveform like this, right. This is the expression for the SSP waveform with a plus sign for the lower sideband and a minus sign if I want the upper sideband. So either of these two is fine. In the coherent demodulator, you will take this SSP signal and multiply it with cosine omega ct, right. That's what the coherent demodulator does, and pass it through a low pass filter. For convenience, let's multiply it with 4 cosine omega ct so that this factor of half and of the trigonometric functions go away. And let's also include a phase offset. In fact, let me consider this as a time varying phase offset, which actually can model both phase offset as well as frequency offset, right. A frequency offset, for example, is a time varying phase offset, right. So a more general expression is write omega ct, which should have been the true carrier frequency, plus theta of t, which models both the phase offset as well as frequency offset, right. Okay, so if I do this exercise, multiply these two, pass it through the low pass filter. It's a very simple trigonometric exercise. I'd like you to do that yourself, and you will see that the detector or demodulator output now after low pass filtering reduces to this expression. Okay. Simple trigonometry, and removing the 2 omega c terms, When you multiply these two, oh, there's something missing here. No one has pointed out. This should be here. There is cosine omega ct here, and there is a sine omega ct here. Right? So you're multiplying these two, removing the 2 omega c terms, and seeing what is left. Right? This is what you will have. That's the result. If theta t is 0, that is, there is no frequency and phase offset, your demodulated output will be same as empty, which is what you want. Right? If you have a perfect synchronism, perfect coherence, output will be equal to empty, the required output. But when theta t is not equal to 0, so in this case you will get a perfect replica of empty, of message. When theta t is not equal to 0, you have a problem. You have a highly distorted signal. Right? You not only have something, the effect that we observed in the DSPSC, but to that you are adding something else, a second component, and this will lead to a highly distorted signal. Right? So that shows that if I use a coherent demodulator for demodulating SSP signals, such a demodulator will be even more sensitive to frequency and phase offsets than the DSPSC demodulation using the same demodulator. Right? So that's something that you have to keep in mind. Now, fortunately, it is possible to effect this demodulation with better tolerance to phase and frequency offset, which can be of course removed by manual tuning, by another method which we shall discuss next time. Thank you.